conference will now be recorded.
That introduction will be missing from the recording. Apologies for that. But the recording will be posted on our YouTube site and is also available on our website. The link is provided in the chat. We do invite everybody to mute your audio, except for Dr. Kolluru. We will accept questions at the conclusion. You can also drop them in the chat if you have problems with your microphone or to be heard well, and you would prefer for your question to be moderated. You can go ahead and do that. So without ado, I will turn it over to Dr. Kolluru.
Thank you. Thank you, Mary, for the introduction, and also thank you, GEOAquaWatch, for hosting this webinar. So the topic of today's webinar is Advancing Ocean Color Science with Cubesat Technology, Seahawk Hawkeye Product Assessment. And this is the outline. First, I'll talk a bit briefly about ocean color and CubeSats, then about the Seahawk mission, which is a CubeSat with the Hawkeye sensor, and how we are going to evaluate the performance of the Seahawk Hawkeye radiometric products, especially the level 2 reflectance products. And then we will take a deep dive into how the performance evaluation is carried out and other aspects. And then finally, if the time permits, I am working on an interesting application with the Hawkeye data, which is super resolution, and then some summary. So I work mainly in passive ocean color remote sensing, which uses sunlight as the main source. Imagine there is a satellite in the space, and the sunlight that is coming onto the Earth's atmosphere, some of it gets reflected back by the sky itself, and that reaches the sensor. And some of it also reaches the surface of the water and gets directly reflected back to the satellite. This is sometimes glint. And the last part, which is the most important one, is the sunlight that is reaching down into the water column and interacting with different optically significant substances like plankton, non-algal particles, and then reaching the sensor. So the most important signal, which is important for the ocean color, is this last one, which is the water signal that is coming from beneath the water surface. So how do we get to this? We have to note that less than 3% of the light from the ocean only reaches the sensor. Land is considered a bright target, but ocean is considered a dark target because most of the light that is coming onto the water surface gets absorbed, and a part of that only goes below the water surface and interacts with different optically significant substances. So in order to get the water plus constituent signal, we need to remove the influence of the atmosphere, also called as atmospheric correction, from the total light that is reaching the sensor or the satellite. So we need to remove the component from this and this to get the last component. We use a geophysical parameter called remote sensing reflectance, RRS, with the units of inverse of steradian, which is roughly proportional to the light leaving the water surface to sunlight reaching the water surface. And this remote sensing reflectance is an important parameter because it is used to derive a variety of water quality products and ocean optical properties as well. One of the major parameters that is derived from remote sensing reflectance is chlorophyll A pigment present in most of the phytoplankton, and this chlorophyll A is used as a phytoplankton proxy. Apart from the chlorophyll A, we also use remote sensing signal as an essential climate variable. So this is just the signal from the ocean without any derived parameters, and this is considered as an essential climate variable. So imagine a sensor in the space, and while it images the surface of the Earth, the light that is coming from the ocean gets recorded in images. This is one such image of an estuary which shows different colors. And depending on the constituents which are present in the aquatic medium, the color of the water changes. For example, we have, because of phytoplankton, we can see that there is a changing color of the water from blue, green to red, depending on the phytoplankton concentration and type. Then we have color dissolved organic matter, which is color imparted to the water by dissolved organic matter. So this is an marsh estuary in Georgia, and it imparts color to the water through sediments or terrigenous dissolved organic matter. And then finally, we have suspended sediments, which depending on the size, shape, and color imparts different color from light brown to red or dark. So all these substances which are present in the aquatic medium, they interact with the light and then impart the color or change the color of how we see the ocean. So logically, we can use the light that is recorded by the sensor to derive information about these substances as well in an inverse way. So ocean color is useful for a variety of applications. One of them is water quality, and I'll list some of the other applications as well. It is also used to provide information about primary production through phytoplankton and chlorophyll A, and also optical properties like absorption and backscattering. It is also used to inform about phytoplankton groups and types, whether it's size classes or phytoplankton functional groups. And a lot of space agencies use ocean color data to study algae blooms and ecosystem dynamics. And through phytoplankton and chlorophyll A, they also use it for ocean carbon fixation. And then for blue carbon, which is seagrasses, marshes, and corals. And then bathymetry. So ocean color has a lot of uses, and there are a wide variety of sensors that are launched by different space agencies to perform the ocean color. For example, this is a chart from Dearson et al. 2023. On the x-axis, you have the number of spectral bands, and on the y-axis, you have the revisit frequency of each of the satellite, which means how much time each satellite takes to revisit the same place. And you can see that there are two clusters here, the one in the black and white or gray, and the ones in color. The difference is these are multispectral sensors, which means they have limited number of bands, 8 to 20, whereas on the right you have this cluster, which is hyperspectral. So you have more than 90 or 100 bands in each of them. And the size of this circle indicates the spatial resolution. So for example, PACE OCI, which is the recently launched one, has a resolution of 1 kilometer. So that's a bigger circle. Whereas DESIS, which is an hyperspectral sensor, has 30-meter resolution. So I'm going to revisit this figure with Seahawk as one of the circles and see where it falls. Today, most of the talk will be focused on CubeSats. So CubeSats are, according to this classification, are sensors which fall in 1 to 100 kg category. So they weigh around 1 to 100 kgs, depending on the size and configuration. And most of the other sensors are either mini or mini to large. So what is a CubeSat? A CubeSat is a miniaturized cube-shaped satellite, and I have a cube here. So this is a 5 by 5 by 5 centimeter cube. Imagine a bigger one, which is a 10 by 10 by 10. So that is considered a 1U or 1 unit. So CubeSats are smaller size shaped satellites, and you can stack these cubes one over the other up to 24 units in different shapes and sizes. And there are a lot of advantages of CubeSats. For example, they can be built rapidly because they are smaller in shape and size. And these are extremely useful to test proof of concept. For example, you're developing a new physical device and you want to test how it performs in space. So a CubeSat is an ideal way because it costs less, as well as it is easy to manufacture and you can test the technology. And if you have a design which is automated, then they are simple to manufacture more as well. And because of their smaller shape factor, they burn in space without leaving a lot of debris in the space when their mission is over. And compared to the large satellites, they are affordable and low cost, and they're easy to manufacture as well because of the off-the-shelf components that are readily available. There are 4 types of missions that are usually carried out while launching these CubeSats. The first is a technology demonstration, which is either to test a method or a software or a device. And then there is scientific research, which is used to test a phenomena, whether how this phenomena is working through from space or not. And then there are a wide variety of educational projects. For example, University of Georgia also has a small sat research lab where students lead development of the CubeSats and small sats. And there are also commercial, which in the recent time has evolved exponentially. So a lot of the planet are CubeSats, planet companies. And these CubeSats, they usually fly in this International Space Station orbit, which is around 400 to 600 kilometers, as compared to other satellites. Coming to the number of satellites launched in until 31st of December last year, 31st December 2025. This is the distribution of the nano satellites launched by all the countries, and United States lead this by nearly 1800. But all the countries are catching up on launching these CubeSats because of their ease to use. And this figure shows the adoption of the CubeSats or nanosats. And with starting from 1998, the first CubeSats were launched in 1998 to 2025, end of December, around 400 CubeSats were launched in one single year. So this shows an exponential adoption of the CubeSat technology because of its advantages. And now coming to the Seahawk, which is an ocean color CubeSat mission. And it is a proof of concept mission to test whether ocean color can be done from a CubeSat. So Hawkeye is the ocean color sensor on board the Seahawk CubeSat. And the idea of this mission is to test the capability to build a low-cost ocean color sensor on a CubeSat. This Hawkeye sensor on board the Seahawk CubeSat, it provided high quality and high spatial resolution imagery. And its design is inspired from the legacy CWIF sensor, which was launched in 1970s. And this mission is currently not operational, but it was launched in 2018. And the first flight was taken in 2019, and the mission operations ended in 2024. The cost for this Seahawk mission is around $1 million for 2 units, as compared to the recently launched space satellite, which is $1 billion. So these are useful in terms of reducing the cost if you want to test a new technology and do proof of concept. And maybe in future there might be a constellation of ocean color CubeSats if we can prove that CubeSats are useful for ocean color as well. In terms of size, Seahawk is around 5 kg weight, and it's the size of a shoebox or a loaf of bread, which is this size. As compared to other sensors which are launched in the previous years, these are all the other ocean color sensors and compared to a normal human being. So Seahawk, with its weight around 5 kg, falls into the CubeSats category, which is micro or nano spacecraft. I would like to revisit the figure which I've shown before, and this is where the Seahawk falls. It has around 8 spectral bands and 16-day revisit frequency and 120-meter spatial resolution. So Hawkeye provides 8 spectral bands with 120-meter spatial resolution, and it had a revisit frequency of 16 days. Launched in 2018, the first engineering test image was taken in March 2019. So the first image was taken on Monterey Bay, California. And this is a true color image, which is made from red, green, and blue bands in the red, green, and blue regions. And on the right is the chlorophyll A image, which is derived from the remote sensing reflectance. And this is around 130 meters per pixel. And below shows the chlorophyll A color bar. Compared to the Modis Aqua, which is 1 kilometer per pixel, we can see that Seahawk produced very clear and crisp features in this coastal region. So it provided very high spatial resolution data as compared to 1 kilometer sensors. During its mission lifetime from 2021 to 2023, it collected around 9,000 images around the world. And this is the most comprehensive high spatial resolution data to date. This is the entire footprint of the Hawkeye CubeSat. You can see that most of these images were in the coastlines around the world because it had some issues with the GPS. So it had to stick with a reference, which is a coastline. So most of these images are in the coastline, and this is the most comprehensive global high spatial resolution data of ocean color inland and coastal waters at 120 meters. The Hawkeye sensor on the Seahawk CubeSat flew around 575 kilometers altitude from the Earth's surface, And this is what a single Hawkeye image looks like. It is around 216 by 720 kilometers in width and height. And this image is acquired on southeast coast of US. And this is where we are in Georgia. It has 120 meters spatial resolution, which means each pixel indicates 120 meter by 120 meter area. And it has 8 spectral bands in the visible infrared from 412 to 867. Some of the unique features of this mission were this sensor did not saturate on coastal or inland waters, and it did not saturate on clouds or ice. Some of the previous sensors, they showed some saturation over bright targets such as clouds or ice, but this sensor did not show such features. And Seahawk had an ability to tilt a bit, so it was used for a consecutive day targeting up to 7 days. So imagine you are going on a cruise and you want to image the same area from the same sensor for 7 days. Seahawk was able to do that. It did not have an onboard calibration, so it used lunar calibration. It did not have an onboard calibration because the size factor is small, so there's limited amount of space on what fits on a CubeSat. So it had to rely on imaging the moon for calibration. Because this design was adopted from the CWIFs, all the algorithms that were designed for the CWIFs were readily applicable, and all this data is also available to be processed through CDAS processing tools. I would like to emphasize and mention that all this data from Hawkeye is readily available and it is open access, and you just need an account in the NASA's Earth Data Search where all the Hawkeye's level 1 and level 2 radiometric products are hosted. All you need is just to create an account in NASA Earth Data Search, and you can search for Hawkeye level 2 and level 1 products and you can download them for free. So now the satellite is its operations are over, but we want to assess the quality of it, not just good images, but how good the quality is of these images. So that's what motivated me to lead this, which is evaluating the accuracy of Seahawk Hawkeye ocean color CubeSat remote sensing reflectance products in different aquatic sites around the world. So consider an image. This is the previous image shown before. This is at 412 meters and it was acquired on 29th of November 2022 in South Atlantic Bight in the southeast coast of the US. And these are all the 8 spectral bands of one Hawkeye image. And in these 8 spectral bands, if you take one pixel and plot the spectra, you can get a spectra like this, which is remote sensing reflectance on the y-axis with the wavelength varying on the x-axis. Although we know that we can plot such a remote sensing reflectance curve, we do not know the accuracy of it, which means we need ground truthing. So how accurate is the spectra and how accurate are the spectra? So in order to understand that, we need to compare this spectra with some ground truth. So that's what we have done here. So we used 2 data sources from Aeronet OC and in situ data that our lab collected in coastal Georgia, and we also evaluated level 2 reflectance products with other associated parameters. So the first data source is the Aeronet OC, and these are all the Aeronet OC sites. These are automated sites where a radiometer is installed in coastal or inland waters, and these radiometers collect the data every day in plus or minus 4 hours of noon. This is a multispectral radiometer which collects data continuously and it is automated. So the data from all these sensors, they go to one single place and gets processed. This is a network that is widely used to evaluate the evaluate level 2 reflectance products, not only from Seahawk but from other ocean color sensors as well. And then we also have some measurements that our lab collected in Georgia coast. These are all the pins which indicate the locations of the data that were collected from our lab using an above water handheld hyperspectral radiometer. So the Aeronet OC is a multispectral radiometer, which means it has 8 to 11 wavelengths spectral bands, whereas we have an hyperspectral radiometer which can collect data at a finer resolution in 340 to 1075 nanometers at 512 wavelengths. So these have more number of data for each point. Using these two data streams, we evaluated the Hawkeye's level 2 reflectance products. So what we did was, if we compared the Hawkeye level 2 reflectance product, which with collocated and concurrent in situ measurements from either Aeronet OC or Georgia coast. So we took the images from the same day within plus or minus 2 hours and compared the data from Hawkeye and the in situ data. So here we have two histogram plots. The left histogram shows the time difference between Hawkeye overpass and the in situ measurement. So for example, if we have 50 minutes, then Hawkeye was within plus or minus 50 minutes of the in situ measurement. And this is the frequency on the y-axis. So we restricted our data to 120 minutes, which is around 2 hours. And then on the right, we have the chlorophylla concentration of all the data points that we collected. So most of them are in low chlorophylla waters, but we have some points where the chlorophylla concentration reached around 10 mg per meter cube. Here we show the Aeronet OC remote sensing reflectance with x-axis indicating the wavelength and y-axis being the remote sensing reflectance. As I have mentioned before, Aeronet OC is a multispectral radiometry network. So we have these multispectral data, and the color of each of these spectra shows apparent visible wavelength, which is a dominant wavelength for each of these spectra. And on the right, we have the hyperspectral radiometric measurements from the SVC, Spectra Vista Corporation's radiometer, similar to the Aeronet OC. But these are hyperspectral measurements, so we have much higher data. And again, each of these spectra are color coded using apparent visible wavelength. This figure shows a qualitative analysis where we compare Seahawk data, which is in purple, to Aeronet OC data in orange color, with x-axis being the wavelength and y-axis being the remote sensing reflectance. Each of these four subplots show four different sites from the Aeronet OC network. And all of these are present in optically complex waters where there is mixed level of sediments and sedum. So, and for each of these site varies from 2, 7, 4, and 3 because on some of these days, even though there is a Hawkeye image, there was a cloud. So we removed all of the data and we ended up with this kind of data. In a first look, we can see that the Seahawk data was able to capture the broad pattern observed with in situ data. So the troughs and peaks observed in the in situ data are also observed with Hawkeye data. So that's a good sign, which indicates that a Hawkeye sensor on a Cubesat can provide good quality of data. This is just a qualitative analysis to see whether Hawkeye was able to capture the peaks or not. This is again a qualitative analysis, but this is for one day. So on 6th of February 2023, our lab was in the field, and this is on the southeast coast of Georgia. And there was a Hawkeye seen on the same day, and there were around 9 points that we took in the field, and each of these 9 points are indicated by the time. So 1357 is in local time. And we compared the Seahawk remote sensing reflectance, which is in the black, with remote sensing reflectance from the in situ data, which is in magenta and blue. So these two are measurements of the remote sensing reflectance processed using two different methods. So there is also an influence of how the data is processed with a method. On a first glance, there is some kind of offset that is observed with Hawkeye data, but as you get close to evening, the Hawkeye data was able to match very well in some places. So this indicates that there is a lot of variability in Georgia coast that can be observed with in situ measurements as well as from Hawkeye data. Now coming to the quantitative analysis, we compared Hawkeye on the y-axis with Aeronet OC and the SVC measurements that we took on the x-axis. And we used two statistics. These are SSPB, which stands for symmetric signed percentage bias, and MDSA, which stands for median symmetric accuracy. So these are roughly bias and accuracy terms. And these two statistics were considered because they were found to be more robust and they operate in the log scale. And the total number of points that we have for combining Aeronet OC and SVC are 79. And here is a 1:1 line shown in the red, and both axes are shown in log scale. This figure is for one wavelength, which is 556 nanometers. In a first glance, we can see that Hawkeye data agrees well with the in situ data that was collected. We repeated the same analysis with other wavelengths as well. One of the important points that we found was in the blue-green region to green region, which is from 488 to 510 and 556, the Hawkeye data, which is on y-axis, agrees well with the in situ data that was collected, with lower bias and higher accuracy. But in the 412 and 447, which is the blue wavelength, we observed that there is a higher discrepancy, as we can see from the spread from the 1:1 line. So these have higher errors from 61 to 43 as compared to these three wavelengths. So we wanted to find why this discrepancy happened in the blue wavelengths as compared to the blue-green and the green region. I am showing only the results for the 5 spectral bands, even though Hawkeye has 8, because the 2 near-infrared bands, which are in 750 and 867, they have some ghosting issues that were observed in some of the images. So we had to remove those, and we have to stick with the first five bands. And the 670 nanometers, which is in the red band, is actually used for the atmospheric correction. So we had to stick with the first 5 spectral bands for our analysis. So the key point is the remote sensing reflectance in the blue-green region matches well with the in situ data, but not at 412 and 443. In order to find out the reason, we evaluated the impact of the associated parameters on the accuracy. So this is the list of the associated parameters that we considered to evaluate the impact on the level 2 reflectance products. For example, taking the chlorophyll concentration, if we replot the same scatter plot shown in the previous slide, but color coded according to the chlorophyll concentration. So these blue points are low chlorophyll concentration, and the red and brown are high chlorophyll concentration. What we observed was the blue points, which are for low chlorophyll concentration, they lied close to 1:1 line as compared to the red points shown here and here, which they lie far away. So this indicates that the level 2 reflectance product is more accurate in low chlorophyll waters as compared to high chlorophyll waters. And this is something that is observed in the previous studies as well. In order to confirm whether this is a real signal or not, we calculated a statistic which is called spectral angle. So unlike SSPB and MDSA, which are bias and accuracy, which operate on magnitude, spectral angle is a statistic which operates on shape. So we imagine you have a reference spectra and you have a target spectra. If you compare these two spectra using spectral angle, if the spectral angle of these two shapes is low, it indicates that the target shape is very close to the reference shape in terms of shape. If the spectral angle is high, they look a bit different. So using this spectral angle statistic on the y-axis, we calculated for all the points. We plotted spectral angle against chlorophyll concentration on the x-axis. So what we found was a not so extremely significant, but somewhat a relationship between the spectral angle and chlorophyll. So this indicates that there is a good match in shape between Hawkeye and the in situ data in low chlorophyll waters. And as the chlorophyll concentration increases, the shapes vary. So this confirms our suspicion that the Hawkeye's products are more accurate in low chlorophyll, and we might need a different method in high chlorophyll waters. We also observed some kind of effect, but not as significant as the chlorophyll A, but there is some kind of effect of all these parameters on the level 2 reflectance product's accuracy. So in order to understand whether we can improve the accuracy of the level 2 reflectance products of Seahawk, what we did was we changed the atmosphere correction to process the data. So briefly, the atmosphere correction process involves removal of the effect of atmosphere in remote sensing imagery, and this involves aerosols, water vapor, and other gases as well. Just a simple view of how the atmosphere correction works is, imagine if you have the same image before the atmosphere correction, and after the atmosphere correction we get more clear image with the haze and the clouds removed from the imagery. In order to understand the impact of atmosphere correction, we took two sites which are representative of coastal and open ocean sites. This is Bahia Blanca, and this is a site in the Aranet OC network, and this is a turbid water site. So this is a turbid water site, as we can observe that there is a peak in the green region in the remote sensing reflectance, and we uh, we we used mum correction, which was initially developed for the turbid and less clear water conditions. So this spectral plot shows the black line, which is the Aeronet OC. This is the ground truth, and the general processing or the standard processing of Hawkeye shown in here, which is in the yellow color. And after a while, there was another reprocessing of Hawkeye data, which is in purple color, and the Hawkeye data, which is corrected with mum correction, which is in the blue color. You can observe that the Hawkeye data, which is corrected with the mum correction, agrees a bit well with the in situ data as compared to the other two standard processings. This makes sense because the mum correction which was used is designed for turbid waters, and Bahia Blanca is a turbid water site. But if you take USC California, which is another Aeronet OC site, and in this site, if you apply mum correction to the Hawkeye image, it deviates significantly from the Aeronet OC in situ data. This again makes sense because mum correction is designed for turbid waters, so it may not work well in the open ocean waters. So what we need is an atmosphere correction which is site dependent and that is catered to the optical conditions observed in the aquatic medium. So the accuracy of a reflectance product depends on a lot of factors, including atmospheric correction being the significant one. So if we have a better atmospheric correction that is designed for a particular optical condition, we can definitely get better level 2 reflectance product, as well as subsequently derived water quality parameters like chlorophyll A, turbidity, and CDOM. One of the other things which motivated us to carry out this analysis is, okay, we have a sensor which can provide high spatial resolution images from a CubeSat, but how well it compares with other ocean color sensors. Because if a sensor, even though if we demonstrated that in sensor on a CubeSat can take images, if its quality is not good, then it is not useful for scientific purposes. So we carried out the analysis by comparing with other ocean color sensors. This is one site and one observation, which is from USC California again. And this spectral plot with wavelength in the x-axis and remote sensing reflectance in the y-axis shows that the black line here is the Hawkeye data, and the red line without any bars is the in situ data. And the other three lines are correspond to different sensors like Modis Aqua, JPSS Swirs, and Sentinel-3 Algae. One of the things which we observe here for this one site and one observation is in 488 to 560 or 670, they align very well, but in the blue region, there is a higher discrepancy. This is a common observation with not only with Hawkeye, but with other ocean color sensors as well. We repeated the same analysis with all the sites and all observations, which is 79 observations that we had, and we show the spectral MDSA and spectral SSPB. So the MDSA plot shows the median symmetric accuracy in percentage, and What we observe here is all these sensors, they have higher error in the blue region, whereas they reduce as you go towards blue, green, and green region. SSPB is a statistic which is biased, so it needs to be closer to 0 to indicate higher accuracy. So this sensor, which is Seahawk Hawkeye, has lower bias as it is closer to 0, which is performing better than other sensors. In the previous slide, I mentioned that if you choose a better atmospheric correction method, you can get better results. So that is evident in this MDSA plot. For example, we reprocessed all the Sentinel-3 All-She data with Acolyte, another atmospheric correction method, and we can observe a reduction in the error by this dashed plot, which is MDSA for the Sentinel-3 All-She Acolyte, as compared to the standard blue line of the All-She. So if we choose a better atmospheric correction method, we can also improve Hawkeye's remote sensing reflectance products. That is something which I am working towards in my next project. So in this analysis, we evaluated 82 cloud-free Hawkeye scenes over 21 distributed aquatic sites with different and varying levels of optical complexity. And the Hawkeye data in 487 to 555 nanometers is more accurate as compared to the blue bands 412 and 443. We observed that Hawkeye's reflectance products are more accurate in low chlorophyll waters, and accuracy decreases towards high chlorophyll waters, but this might change if you use a different atmospheric correction method. With an appropriate atmospheric correction, we found that Hawkeye's RRS can be more accurate to 15% MDSA at 488 nanometers. And we also found that Hawkeye has comparable performance with other ocean color sensors as shown in the previous one. So this analysis is extremely useful for CubeSats, and it is a proof of concept demonstration mission to show that we can perform ocean color from a CubeSat. Some of the applications or future for this Hawkeye is, right now, all the Hawkeye's level 2 products are available to free in open source, and they are free to download from the NASA's Earth Data Search website. And when you download the level 2 reflectance product, you will also get chlorophyll A, which is the phytoplankton pigment proxy, and KD490, which is a measure of water transparency or water clarity, particulate inorganic carbon, and using some band methods, you can also derive particulate organic carbon. All these are readily available and you can download them for your area. The Hawkeye, because of its high spatial resolution of 120 meters, is especially useful in inland and coastal waters, where if you want to image a narrow river, it gives some data as compared to coarse resolution sensors where you do not get enough data. The Hawkeye's data is also useful to improve other sensors. So that's what I'm going to talk in the next few slides. This Hawkeye is a baseline for constellation of ocean color CubeSats. This study shows what's the potential of CubeSats for ocean color, and if some space agency or if there's an interest, then we might see a constellation of ocean color CubeSats in the future, which can complement existing sensors data. So what are the advantages of high spatial resolution? So in small and narrow rivers or in some coastal waters, we can detect small scale features which might be absent or which might get too coarse in coarse resolution data. So having high spatial resolution, you can detect small scale features. For example, in this algae bloom in the Arabian Sea on the west coast of India, or you can use it for improved coastal and inland water monitoring and better delineation of plumes and blooms, how well and how long the plumes are extending and how they are sustaining. We can use high spatial resolution data for better delineation, and we can also use this data for land and water discrimination. So Hawkeye, with its high spatial resolution of 120 meters, is extremely useful. But how? So, for example, imagine a small feature in the Arabian Sea, which is an algae bloom, and this is how I call it an eye. a small feature in the Arabian Sea of an algae bloom looks like, which is 27 kilometer by 54 kilometers. This is an algae bloom, and the colors show the chlorophyll concentration in mg per meter cube with the color scale at the bottom. And the same eye with the Hawkeye looks like this. Imagine the level of detail that the Hawkeye shows here. The features are clear and crisp with the Hawkeye because of its high spatial resolution. So we got into the idea of whether we can improve the resolution of Sentinel-3 Algae to Hawkeye resolution, because Sentinel-3 Algae is an sensor. The Algae sensor on Sentinel-3 satellite provides ocean color imagery from 1 to 2 days around the globe, whereas Hawkeye is a targeted sensor which provided data in select locations, and it was able to collect 18 scenes per day with limited amount of footprint. So if we can combine the strengths of both these sensors, we can get global high spatial resolution of Algae at 120 meters. So that's what we are trying to do here. Super resolution is an application wherein we transform low resolution data using a deep learning model to high spatial resolution data. So this is a low resolution data or coarse resolution, whereas on the right is an high spatial resolution data. And deep learning is a widely used methodology, and there are a lot of models that can be used to do this. We chose bicubic, which is an interpolation model. This is not a deep learning model, but a standard model, statistics based model as a baseline. And we developed two models, VDSR and EDSR. These are two deep super resolution networks that are used to transform low resolution data to high resolution data. And we chose Sentinel-3 Algae because this Algae has spectral bands which are very close to Hawkeye, and this is the next best resolution after Hawkeye in terms of ocean color with 300 meters. So we developed two models, VDSR and EDSR, but I'm showing the results for VDSR and bicubic here. On the left, we have Sentinel-3 Algae at its original 300 meter resolution, and this is a coastline with some features in the coast. And the VDSR model was able to produce high spatial resolution data with crisp and clear features. And you can see the difference from 300 meter to 120 meters, as well as the bicubic. But bicubic lost some of the features, as you can see here and here. This is another snippet of the image, which shows that the VDSR is a deep learning model that is able to capture the crisp and clear features, reproduce them from low resolution data to high resolution data. So Hawkeye's data at 120 meter resolution is used for the development of this model, and we are going to submit this soon to a journal. And this model can transform the low resolution 300 meter Algae data to 120 meter high spatial resolution data, which is extremely useful for continuous monitoring and high spatial resolution data. So to summarize, the Hawkeye's ocean color data is comparable with other ocean color sensors, and the atmosphere correction can improve accuracy of Hawkeye's products depending on the site. And finally, we also have Hawkeye data that can be used to improve spatial resolution of other sensors. Some of the potential applications of Seahawk are we can extend the super resolution data to improve Morris and Pace data as well, to bring it to 250 meters and 500 meters as well. And the products again are available to readily download on NASA's Earth data site. With that, I would like to conclude, and thank you.
Wonderful. A virtual round of applause for our presenter. Does anybody in the audience have any questions? Dr. Abdul Ghaffar asks, can we use Hawkeye to measure other water quality parameters other than ocean color? Does it have any other sensors on it, I think is what he's getting at.
Okay. Hawkeye is just one sensor on the Seahawk CubeSat. There are no other sensors on it. So we can derive water quality parameters like chlorophyll A, KD, turbidity, PIC, POC, but not others like temperature. Yeah, if that answers the question.
Hopefully it does. Any other, yes, Sarah mentions that you can treat it like a CWIFS image. Yeah. Any other questions? You can unmute and ask your question out loud. You don't have to use the raise hand feature, or you can drop it in the chat. Dr. Ghaffar has a follow-on. Would you suggest, and do you have any other options to suggest? I guess that's what he's saying.
Apart from Seahawk, like or sensors that measure other parameters like Seahawk, is that the question? Or is there any other sensor like Seahawk which is currently operational? I'm not sure, but
Thank you, Srinivas. Am I allowed to speak?
yeah.
Yes, go ahead.
Thank you, thank you. So I was wondering, since one of my students is working on analyzing few water quality parameters and using the Centennial tree and available data sets on Google Earth Engine. So I was impressed by the presentation using the Hawkeye, but there are a few limitations you just already mentioned. So, for example, we wanted to analyze the water quality parameters for a particular river or a water body, and we also wanted to make it precise that the data sets and the analysis that we are observing through this spatial analysis is more accurate and close to the conventional methods. So, would you share some insights based on the other models or the things you have used, or someone may like to share?
So for the rivers, since your focus is on the rivers, I think more high spatial resolution data like Landsat and Sentinel-2 also might work, but it doesn't have the ocean color bands like the Seahawk or Sea-Waves. Yeah, I am not sure. If you're looking into the super resolution, then that is possible, but you can improve the resolution from 300 meters of Sentinel-3 ALG to 120 meters of Seahawk. That is possible with some deep learning models. And also, I think Seahawk is also not available on Google Earth Engine, but it's available on NASA's Earth datasets. And I would like to know more what kind of analysis and the parameters that you're looking into. So yeah.
Thank you very much, Srinivas. We are looking for a few parameters like initially the physical and chemical parameters. Like we can also measure the BOD and COD using some indirect methods, and we are facing the correction issues as well. Particularly, the cloud cover is also an issue. Just like you mentioned, we use the Sentinel tree using this Google Earth Engine, where we have the data sets available for a particular time zone. It's limited to particular um, time when the satellite moves on. So, like in the Hawkeye you mentioned, you have the data sets for like 30 times for a particular area in one day as well. That's impressive. But we are also looking that if we go for the on ground analysis for particular parameters to compare, and we also do not want to have the cloud issue. So for that, maybe some deep learning models would help, but certainly it would have the cloud issue as well, that if the data is not properly available, we may face challenges in the fine tuning the data sets. So thank you so much again and it was a really impressive presentation. Thank you so much, Mary, as well.
Thank you.
Of course. Any other questions? I did see the chat with a couple questions we can go to, but I want to defer to anybody who's in the audience first. Okay, I'll go ahead and ask mine in no particular order. Have you done your quality analysis? I may have missed it on any or all of the freshwater scenes available through Hawkeye. If so, are the results similar?
So the analysis that we carried out also included some freshwater sites. For example, we had some data from the Indian River Lagoon, as well as some lakes in the Europe. But these are from the Aeronet OC sites. We did not collect any in situ additional data like the one we did for Georgia coast. We did not do similar things for freshwater sites around the world, but we had radiometric data from Aeronet OC sites which were installed in the freshwater sites. And this is a combined analysis, and we did not look into an individual inland waters only analysis because we did not have enough points that satisfied our criteria. And we had a very good quality analysis and quality control so that we can compare with other ocean color sensors. So a lot of points got filtered out. Yeah.
Great, thank you. My second question, which might be helpful to folks like Dr. Ghaffar, are there any, is any of the data that's available in the NASA repository, does it include, are they already pre-processed with your Acolyte correction as a data set, a downloadable image, or is it only the uncorrected data available
so NASA
as packages on the NASA?
Yeah, so NASA produces these level 2 reflectance products, and they are corrected with their standard L2 Gen system.
Okay.
But they are not processed with Acolyte. But I am working on processing all the data with Acolyte, and maybe in next few months or by the end of this year, we might have some results with Acolyte as well and see how it works. But right now it's only NASA's L2 Gen, which is already atmospherically corrected. And it also includes some parameters like chlorophyll A, turbidity, sorry, KD, chlorophyll A and PIC with the level 2 products included. Yeah.
Sort of to follow on what they provide for PACE too. So.
Yeah.
Okay. My last question is, in coastal regions at the 120 meter resolution, what is the distance of the coastal mask away from the coast? Like, how much of the true coastal region do you lose because of the coastal mask? And then does it capture, do your Hawkeye images still capture any features like seagrass beds or oyster beds?
Okay. If this, for your first question, which is how far, coastal mask. I do not have an exact answer for that. We also had some GPS issues with the Hawkeye data, so I do not have an exact answer on how many meters it is exactly.
I think it could probably be assumed to be 1 pixel, right? Which would be 120 meters.
Yeah, 120 meters.
Okay.
And to answer your next question, it might have, we had some scenes over Florida's coral reef region, and we can see different features there, but we did not go into and analyze whether how good they are, but we can see the colors. And it has good number of pixels in the Indian River Lagoon as well, where we have the seagrass beds. I'm not sure about the oyster beds, but we can see some seagrass features there as well. Yeah.
Okay, great. Sarah made a couple points in the chat. She says you can download level 1 data and process it with whichever atmospheric correction you want. That's in the NASA Earth data portal. Yeah. And she says Hawkeye does not saturate over land, so you can still access that data as well. inland waters if
Yeah.
it's applicable
Yeah.
to you.
Thank you, Sarah.
So, any other questions or comments from the audience? Okay, just a reminder, we did record today's, except for the introduction. Sorry about that.
Okay.
It will be available on our website probably sometime tomorrow. It may be there a little later today, but anybody in Europe might be asleep whenever it gets posted. But for sure, you can check it out tomorrow. We do want to make everybody aware that we, our Early Career Society, is featuring 3 talks. They're called Water Talks. This is our 4th year for the Water Talks. And we're doing it all in one day now, March 19th, which is the week before World Water Week. At 12 o'clock UTC is when the very first talk will be. We will have all 3 presenters that day, and you can find out more about their titles, their speaker bios and whatnot on our website. And same spot where you can find out about upcoming webinars as well as past webinars. So thanks very much to Dr. Kolluru for your presentation today.
Thank you, Mary, and thank you, GEOAquaWatch, for the opportunity. Thank you.
Of course. Wonderful to know the high resolution data is so available. So thanks everybody and have a great day, and join us for the next GEOAquaWatch meeting. Thank you. Great job.